Good.
Okay.
Very good.
So thank you, Fabian, for this invitation. And well, the title you assigned me, then I think I won't go much into the multi messenger stuff, and instead I will concentrate on giving you an overview of gamma reverse, where we stand, let's say, about major stuff about these sources. Okay, so as an introduction, I think it's good to have a kind of view of what are gamma reverse, and this is a slide that tries to summarize the 50 years of history. 50 years. I mean, same age of somebody in this room, I think, not that many. So, as you know, I mean, these are major steps forward in understanding these sources, ranging from let's say, understanding that their hypertrophic sky distribution coupled with the observation of their fluxes were hinting for an extragalactic origin of the sources, confirmed with the discovery of the afterglow. Then, soon after, the first identification of the supernova associated with the long gamma reverse probe of the possible projectile path. Then, with the launch of SWIFT in 2005, the discovery of the quite complex behavior in the early phases of the emission of these sources, specifically the X-rays. Then we arrived to 2008 with the Fermi, which opened the, let's say, 100 of MeV up to GeV energy range, showing up that this range most often the emission is dominated by the afterglow. And then we have the fantastic discovery in 2017, the let's say gamma reverse entering the multi-messenger domain. And finally, last but not least, in 2019, at the opening of another observational window, which is in the ranges up to the TV energy range, where we can probe probably the most extreme processes of which pertain to the acceleration of particles and emission in these relativistic sources. So this is all my introduction, and this pretends to be a cartoon that summarizes what we have understood in these 50 years about these sources. Now, more or less, we can tell the story this way. We think there are two pathways that are the progenitors that lead to the gamma reverse, in the form either of the collapse of massive stars, thought to be progenitors of long GRBs, or the merger of compact objects in binaries having at least one neutron star. The possible evolution of this system leads to a quite similar, let's say, configuration where you have the formation of a central engine, either a highly spinning black hole or highly magnetized and highly spinning neutron star, which are able to power a jet, which has to expand within the stellar environment of the projectile until it breaks out and it really accelerates, reaching large velocities, relativistic velocities, with wherein we may have then the dissipation of energy, internal dissipation, which gives rise to the prompt emission, and then the deceleration of the jet outwards, which gives rise to the output. So, if we think about cooking a gamma reverse, these are the 5 fundamental ingredients we have to say: a progenitor, a central engine, a jet, a prompt dissipation emission mechanism, an afterglow dissipation emission mechanism. And I will try in the rest of my talk to go through these 5 points in a very general way, trying to highlight where we stand and what we do not understand. So let's start with progenitor. So here you see in these boxes, let's say, the arguments or the observations that, let's say, on which we stand, stand the division in short and long gamma reverse with respect to their progenitors. I think a very simple argument to understand this idea comes from the fact that if you work out the duration of the burst, providing that you set in the relativistic correction, you realize that the GRB duration should be similar, of course, modulo the redshift correction, to the duration of the central engine. So if the central engine is an ultra-fitting black hole, you have the central engine itself might be related to the free fall time. And the free fall time is inversely proportional to the density of the material that falls onto your object, to the square root. And so I'm missing one. Well, it's an effect, yeah. So if you work with typical time scale of long GRBs, you realize that you need some mass which has a relatively low density, so typical of massive stars with relatively large radii, whereas if you go to the short duration time scale, typical of short GRBs, you realize that the density you need is quite large, typical of neutron star. So this is a simple argument that motivates the distribution. But of course, now we have a lot of observations that prove this is indeed the case. However, as Marika showed, the, let's say, short and long divide that for, I would say, almost 40 years was the standard paradigm in GRB studies was a bit challenged by, I would say, the last 4 years because so let's start here. There were examples like this first, which apparently is a short duration GRB, but when you look to the other features like its spectrum or the properties of its hot galaxy, they are not typical of short GRBs, but resemble those of long GRBs. Most notably, there is in this event, in the Astro-COLIBRI optical light curve, the appearance of the bump at about 30 days, which is brighter than the typical kilonova that we would expect if this were a short GRB, and it evolves slower than the typical kilonova evolution. So this is interpreted as the signature of a supernova event in a short duration, in a apparently short duration. So this poses the fundamental question, among others: how is it possible that a collapser is producing such a short duration event? One possible explanation is the following. If you remember my previous slide, you have that when the jet is produced, it has to travel within the ejecta of the massive star, which were probably torn away and which are expanding. And in this, the jet spends a lot of energy and equivalent time. So when it breaks out, it might be in the condition in which it has a short duration because it has still only a few hours to spend. So the short duration is due to the fact that the jet spends most of its time scale, let's say, in piercing through the environment. The other way is here. So here, the person Mario already presented. It was an apparently long duration theory, but again, the optical signature of a too faint and too fast evolving supernova, if it were a long period, which is instead interpreted as a kilonova. And now, this event, like the other one that mentioned before, 230307A, poses the opposite question. How is it possible that from a merger of fine neutron star, I can sustain the emission up to tens of seconds? And here, I would say that there is still no clear answer. There are some proposals, some playing with the nature of two objects. For instance, if you simply work out the threefold time argument before, you may play with the density, arriving to have something which is less dense than neutron star, probably white dwarf, or there are other proposals that play with the dynamics of the accretion disk, which in this system might not be accreted immediately, but let's say over a time scale which can be as large as tens of seconds. Okay, second ingredient, central energy. Here, yeah. So what we need, if we want to explain a gamma reverse, is that the central engine should produce a coordinated jet with enough energy. The jet should reach bulk velocities with values around 100, and it should be long-lived. Now, one possibility, which seems to be natural in massive star, is the production of a black hole directly or through a short-time scale existence of a kind of neutron star. Now, the issue here, or the idea, is that then you need to extract the energy from this system. And there are possibly two channels. One is a neutrino-antineutrino annihilation, which has its maximum cross-section along the jet axis, and it depends on the accretion rate and black hole properties, mass and speed. The other possibility, which is much better for some reasons, because neutrino-antineutrino has some, let's say, maximum value around 10 to the 52, which is not, compared to the dispersion of the energetic we see in GRBs, it doesn't cover maximum values. So the other possibility is to extract also the energy of the rotating black hole through the magnetic field, which is anchored to the disk. And here you have a strong dependence on the property of the system, which goes square with the magnetic field intensity, spin, and mass of the system. So in general, I think we are quite well satisfied with this kind of central engine, especially for long GRBs, except for the fact that if the black hole accretes too rapidly, you end up with having finished or exhausted the fuel compared to some GRBs, which can last thousands of seconds. Or if you want to interpret in a normal long duration GRB, the extended emission that is observed in the X-rays up to thousands of seconds. There are, however, let's say, explanations in the literature. I'm just mentioning some here. Don't have time to go through them. Let's go to the other possibility. Another possible central engine is magnetar, which is a scenario which can be produced, especially could be in the case of binary mergers. You could have either a phase in which you have a highly spinning star, from where you can efficiently extract the energy, at least via two mechanisms, which is to spin down the luminosity of the system until it remains like that, or even accretion onto the magnet itself, which of course, I mean, is threatening the mass, which can eventually collapse into it. Now, the positive point is that in this case, you have that most of the requirements are satisfied, except the fact that recent numerical simulation seems to show that the jet which can be launched from this system is not reaching that much large velocity. So if the requirement, one of the requirements to avoid the fact that the gamma rays produced in the jet are totally absorbed by themselves due to the high opacity, it's that the jet is moving with high batch velocities relatively. So if you want to solve this issue, you want gamma of the order of 100, and here it seems that it's not that much. So this is the situation. Third ingredient, the jet structure. This was mentioned also before. So we naturally expect that gamma ray burst jets have a structure in the sense that their properties depend on, for instance, the polar angle. Okay, and this is of course natural, because if you think about the jet, it doesn't. It's not born in a completely vacuum ambient. It is born near the central object, and it has to expand within the environment, whatever it is, the stellar environment or the ejecta material. In this vision, in this path, of course, NHD instabilities are going to interact with the jet boundary and produce, for instance, a distribution of energy and velocity, which depends on the angle. Here you see simulations of collapsar and DNS physics, where we see the isotropic energy contained in the jet as a function of the angle from the polar axis, from here down to here. And you see that typically these systems produce a region, a core, what we call a core of the jet, where energy is constant, and then it decays with power loss, which in this case is a rate of the order of theta to the minus 3. This holds both for the energy and for the other factor, which is important, which is the vital influence factor. So, why this is important? For many reasons. I think one of the most interesting is the fact that when you look to the energy, I'm going to pass that much time ahead. When you look to the energetic of GRBs, here from the emission of the GRB, as a function of the energetic of the associated supernova, these are long gamma rays, I think it's striking to see that the supernova energetic are clustered around within 1 decade or so, whereas the GRB energetic are distributed over several orders. And this is true if you compute, let's say, the isotropic equivalent energy, forgetting that there is a jet, but it's also true if you correct somehow for the presence of a jet, which are the respectively flat and the blue points here. So what is the interpretation? If the jet is structured, we can somehow ascribe some of the diversity that you observe in GRB due to orientation effect. So I see the jet under a certain angle, and it is state of random orientation in the plane of the sky. And naturally, you may imagine that as much as I see along the axis, I see a powerful source. When I go off axis, due to relativistic beaming, I do see a softer and less luminous. So this is intriguing because, for instance, we started studying this back in 2005 in the field of papers. And if you look to the luminosity function of gamma reverse long one, okay, so the point here represents the tenfold luminosity function with real data, which is extended down to where we typically put our low luminosity GRBs. We have a few of these, but we can correct for the fact that we are efficient in localizing that, and they are detected only at low redshift, where the volume of the universe is small. Well, after playing with possible selection values, you have something that you can try to reproduce with the model. And here you see that a structure jet is well describing let's say, consistently the full population of GRBs from high luminosities down to low luminosities. What we found is that a Gaussian jet or a highly structured jet, let's say with alpha power or alpha smaller than -4, is consistent with this data. The idea is that then what we observe today, and we have been observing in the majority of cases, are jets within their core opening angles, and in few events we have detected the jet off axis. For long gamma reversed, I would say that apart from these statistical indirect evidences, I think there are only still a few events for which there is the claim that the jet is structured. One of these is the boat one, that probably the brightest of ever seen. But so the situation is different for short GRBs. I think in that case, we had the first fantastic event in which we have the proof that the jet is structured. So it's different there. But we can play it. So I won't say anything about this because Marika fantastically explained it. I would like to draw your attention on the fact that we can play this statistical argument on the, let's say, population study in a structured jet scenario with short GRBs as well. So here you see the result obtained by assuming that short GRBs have a quasi-universal jet. Quasi means that it's not exactly the same for all the sources, but you allow some parameters to have some distribution. And what we find is that we can reproduce the properties of GRBs detected by Fermi and Swift if the jet structure is like this. Here you see the luminosity as a function of the angle and the peak energy of the prompt emission spectrum as a function of the angle, of the polar angle. So with these two structures, we are able to reproduce what we observe, and nicely, these two structures are also consistent with the posterior distribution of the structure that we derive from the modeling of the afterglow and imaging in the radio band and proper motion of 1707. Okay, so fourth ingredient, prompt emission. When you look to the prompt emission of gamma reversed, there is one thing you can measure, the variability, that is small, milliseconds, meaning that the dissipation radius is small, 10 to the 13 if you play causality argument. Second ingredient is that the luminosity and other arguments suggest that the magnetic field in the emission region should be large. So these two points, let's say, imply that we think about synchrotron and synchrotron set content as the leading emission mechanism in the emission region, which produces the gamma rays. However, when we go to the observations, sorry, there is an effect. So what you can do very simply is to calculate the cooling time scale of accelerated particles, thinking about electrons primarily producing the emission radiation you see. And the cooling time scale basically depends on some parameters, notably the magnetic field in the emission region. And if you set in typical numbers, you have that this number is of the order of 10 to -8 compared to the variability or dynamical time scale of the system, which is of the order of a few milliseconds. So this means that electrons are accelerated in the shock, but should cool very rapidly. So synchrotron cooling says that the part of the spectrum below, let's say, the characteristic frequency, above that, you depend on the slope of the accelerated non-thermal particle distribution, but below that you have a fixed prediction by synchrotron emission, which is that the spectrum in photons or in nu that is minus the half in photon and 1/2 in nu in SCD representation. And as you can see from this plot, this is one example, but there are many. The spectrum that is observed by any satellite going from Compton Gamma Ray Observatory up to Fermi, the spectrum is always, in most cases, harder than what the theory predicts. So this was, for years, the major problem in understanding the prompt emission of these sources, called the synchrotron deadline. 2 minutes. Okay, so the possible solution came by going back to the data, analyzing Fermi and bursts, where we discovered that the spectrum is a bit more complicated than what we thought before, due to the appearance of a break below the peak of the nu. And as you see here, we found that in several bursts, the slope between the break and the peak and below the break is consistent with the slope that synchrotron cooling predicts. But the cooling is only marginal because, as I showed you before, we do expect the cooling frequency to be down at radio wavelength, but instead we measure it at the TVN. So this means that electrons do cool, but not that much efficiently, meaning that the physical situation in the emission region is more complicated than what we think. And actually, you can prevent electron from cooling if you increase the magnetic field value, but if you do that, you would have an inverse constant component which is quite bright and should be detected by LAC, which is not the case. You may, on the other side, move the emission region at large radii, where if the magnetic field is affected, you have naturally a low magnetic field. You solve that problem, but you lose the variability. There are other options, among which the fact that the emission is not due to electrons but protons, for which the cooling time scales with the ratio of the masses to the strong column. Afterglow. Can I take just 1 minute more? So afterglow modeling is quite complex. We have several parameters there, which in a way encapsulate the ignorance of modeling in details the physics which happens there. We have a set of intrinsic parameters describing what happens in the shock, such as the fraction of energy that goes to particles, magnetic field, how particles are accelerated, and the fraction of particles which are accelerated. But we have also some extrinsic properties, such as the orientation of the jet, again, if it is structural or not, and the density in which it expands, which determines the dynamical evolution of the jet, okay, the typical in the ambient medium dense. So there is a lot of parameter generacies. I would say that we have learned in the recent years that the best way to understand the physical parameters, measure them, and break as much as possible the degenerative is to put together as much information as possible, which is now happening, of course, for the most notable GRBs, where you can have dense sampling in frequency and time, such as, for instance, this burst is very well known for the view here. It was detected up to TV energies by tests. Here you see the modeling, which incorporates both reverse and forward shock, synchrotron and inverse quantum cooling. And what we could derive is that we have a good, let's say, determination of the parameters. Among them, we find, which is not new for reverse detect emitting activity, a quite low fraction of energy going to the magnetic field. So I skip this one. This is my last slide. Another example in which I think that the efforts are relevant is this burst. I don't know those of you who've been here last week, probably you had a review on this event here. I'm just quoting some of the most notable things about this burst. Of course, it's rare, one every several thousands of years. But I just want to mention this last point here. Because it's very fresh. So what we could do, in this case, exploiting radio observation, is to measure the evolution of the size of the burst. It is the second ever burst in which the size measurement evolution is possible. The other one is 03. We go back to 2003. So what we measure, thanks to radio VLBI observations, with both European and US antennas, is the evolution, as you see, of the size, is the projected size in milliards seconds in the plane of the sky as a function of time. This is a long observation, as you can see from the data. I mean, we followed this event up to after years. What is interesting is that from you do not well, first of all, the detection is significant, but if you look to the colors, you see that probably there is a different size evolution, a different frequency. This is consistent with the fact that if you look to this event in the radio, probably also the different frequencies, here 50 gigahertz and 5 gigahertz, are dominated by two emission components of the external shock, which is the reverse and the forward shock itself. And that's it. Sorry for the.